Alright, so now we're getting into the fun stuff. This is the op-amp I designed as a MOSFET replacement to the BJT-based design of the LM386, which is an infamous audio amplifier. I wanted to go over the circuit just a little bit. So we've got a negative feedback configuration loop here. We've got the voltage applied to the V plus terminal, which means we've got non-inverting configuration. The gain is set by R1 over R5, so 20K divided by 1K, which is 20. So our gain here is 20. I'm sweeping the supply from 4 to 6 volts, so this is VDD here. So I've got that parameterized in this dot step param from 4 to 6 volts in 1 volt increments. So that means that we are going to see 3 waveforms up here when we run the simulation, but ideally they should all be the same. So we shouldn't be able to detect the difference between what the simulation looks like at 4 volts and what the simulation looks like at 6 volts. So let's take a look here at the circuitry at the non-inverting node. It might seem a little weird, but hopefully it won't once I'm done explaining it. These 2 resistors here, R3 and R4, are simply a voltage divider. So we're taking in VDD, whatever that may be, depending on the step. And because these 2 resistors are the same, it's just going to take 1/2 of whatever that voltage VDD is. When you're dealing with a differential input amplifier, you always want to bias the V plus and V minus terminals at 1/2 VDD. Ideally, the op-amp will completely ignore that voltage and will only allow this small signal AC source that we've got here, or whatever is different between the 2 nodes, to go through and be amplified. So here, if our VDD, once it gets to 5 volts, this node will be at 2.5. Since V minus and V plus are equal, it also means that V minus will be biased at 2.5 volts. This big capacitor here, you can think of it as a DC blocker. If there was any sort of DC component to this voltage source here, it would just be blocked out here. So we can specify that in, so if we go right click, and we go to sign, we have this DC offset of 0, and we don't have a DC value there, but if there was a DC value, that 10 microfarad capacitor would block it out. And so if we look at the V out here, the output, so why do I have an 8 ohm resistor here applied to the output? Well, this is called the load. And the load is 8 ohms because a speaker is typically 8 ohms in resistance. So if we've got a gain set at 20, our input voltage is 1 millivolt. So that means our V out should be 20 millivolts. So let's sim it and see what happens. Alright, so I'm just going to go ahead and pull these down first. Sim it again. There we go. And we'll take a look at the output. Oh, well, actually we're not going to take a look at the output because I did a .AC analysis, and we want to look at a tran first. So let's go to a transient analysis. We'll do a stop time. So let's get like a solid 3 periods. So we have the frequency of the sine wave set at 1 kilohertz. So if we run it for 3 milliseconds, we should see 3 periods. But I'm going to stop it at 8 milliseconds, and then I'm going to start saving the data at 5 milliseconds. And this way, we don't get any of like the weird effects that happen right at startup. So change that. And another thing that's part of the simulation, this .4 operating point here, this is how we're going to find the total harmonic distortion. And I'll show you how to do that. And you can only find the total harmonic distortion or use a .4 if you're doing a transient analysis. So it wouldn't have even worked if I had tried to run the AC analysis to begin with. So we'll probe V out. Oh, we need to run it again first because that's still the AC. There we go. There we go. Alright, so if we look here, sitting pretty with the peaks of all three of our waveforms, which are almost identical at 20 millivolts, which means that our gain was set correctly. Our output is outputting as expected. So if I wanted to zoom in, let's say this right here, I just want to see if I can detect the subtle differences. No, I can't. So if I go to, if I right click on the waveform viewer and I select steps, you'll see that I do have all 3, 4, 5, and 6 voltage for VDD plotted here on the same plot. So it is just that the output is performing that well. Okay, so now let's see what our total harmonic distortion is for this LM386 model set at a gain of 20. So when you do a .4, what you have to do is go to View, Spice Error Log, and then you're going to scroll all the way down, and then here you're going to start seeing harmonic frequency for your component, and the total harmonic distortion is at 0.42%, so a little less than a half of 1%, which is excellent. The data sheet for the LM386 lists the total harmonic distortion at 0.2%, so this is about a quarter of that, which is excellent. The lower the total harmonic distortion is, the better, and you can even see if there was some harmonic distortion, the tops of these peaks here would be clipped and they'd come across as straight lines, and we might be able to see that when we increase our gain, or if we were to increase the voltage here at the input. So, but that's how you find your total harmonic distortion, is you go to View, Spice Error Log, and then you'll see it listed here. Alright, so that all worked out really well. And all of these simulations, as well as how I set up all of these circuits, are included in that download in the tutorial. So let's get rid of this one. Yes. Let's look at the gain of 200. So here it's the exact same circuit. The only difference is that the resistor and the feedback has gone from 20K to 200K. So that when we do 200K divided by 1K, we get a gain of 200. We still got our 8 ohm speaker load here. And let's simulate it and see what happens. Yep, so we've got our 1 millivolt input, gain of 200, and our output is at just under 200 millivolts here, but it gets closer as time goes on. So let's see what happens at 5 volts. And it's the same. Okay, so we're still getting good output. We're not seeing any clipping. But now I want to see what happens if we increase this, just so that I can show you what it would look like if you didn't have very good total harmonic distortion. So this is exactly what I'm talking about. So you see here how it kind of clips it at the end, and it shouldn't do that. Well, no, it should do that, but you don't want it to do that. Now if we were to go to the View Spice Error Log, we're going to see the total harmonic distortion at something crazy, probably like 20%. Oh, it's actually still not that crazy, it's 6%. So while it may be audible, it doesn't seem like it would be that big of a problem still. Now if we were to increase the load, let's say we had a 4 ohm speaker on there, this just might totally break it. Yeah, and it does. Not only do we see a major reduction in the gain, but that clipping gets much worse. So now let's take a look at the harmonic distortion. And there, now it's at 16%, so that's terrible. You don't want to do that. So when you're considering what types of loads to put on, it's like in the example that you'll see in the next section of the tutorial, I made a 3M or an LM386 based audio amplifier for my guitar. So I built like a portable mini guitar amp. And there's no way that I would be able to use a 4 ohm speaker, get the output that I need, and there would be an audible difference between what I'm playing and what you hear. So now let's take a look at the AC analysis. So I'm going to change this back to an 8 ohm load. Move this back down to 1 millivolt. So the .4, this is the total harmonic distortion, is not going to work with a .AC analysis. So you can just comment it out using a semicolon and it won't worry about it. Now I'm going to click on the .tran and I'm going to change this to an AC analysis. So I'll do a decade, number of points per decade, I'll do 10, starting frequency of 1, and I'll go out to, we'll say 2 megahertz. If I need to change it, go out a little bit further, I'll do that. Alright, so considering this is an audio application, this makes me extremely happy because I've got here a stable flat line from 10 hertz all the way out to, let's just see where the 3 dB frequency is. Ah, no! So if we are at 45, so we'll go down to 42. I don't know. Cursor 2. Okay. So that corresponds to 75 kilohertz, which is well above the audio range. So if we were to push this in a little bit to, I'm going to say 20 kilohertz, which is going to be, I mean, the sound of a mosquito is like 9 kilohertz, so anything above that is just going to be fairly annoying and very, very high-pitched. But you can see that the gain is this nice flat line, which is what you want to see for an audio application. So there's our gain of 20 and our gain of 200. Let's go ahead and exit out of those. Go ahead and save that for you guys. So now we're going to get into common mode rejection ratio. So this is going to look a little funky at first. All that I'm doing here is it's the exact same circuit. It's the same op-amp part put down twice, configured in a different way. So it's the same input and output, but with a different configuration in each. And then when I take the ratio of this V out divided by this V out, that's going to give me the common mode rejection ratio. That's going to tell me how much of what's common is not being amplified in that signal. So you want the common mode rejection gain to be very low, and you want the common mode rejection ratio to be as high as possible. So if we run this simulation, this might take a second. We've got quite a bit going on. So we're going to take this output, we're going to divide it by the voltage seen at V out D. Oh, that's terrible. What happened here? I think I did it backwards, that's why. V out D. There we go. That's how it should be. So V out D divided by V out C. So V out C. Yes. Okay, so that looks much better. So before we were looking at like a negative value, well, which actually isn't a negative value, it's just a decimal. But from up to, 1 megahertz, we're looking at over 200 dB. So the common mode rejection ratio is extremely high, which is what we want. So this actually has very, very good common mode rejection ratio. And we saw that because if there was any sort of offset between V plus and V minus with that bias of 2.5 VDD when VDD is 5 volts, we would see that DC voltage amplified through to the output, which we didn't. So that's kind of like how you can understand, you know, if you have an input signal and your output signal isn't just like a perfect amplification of that input signal, that's how you know that you don't have very good common mode rejection ratio. So let's get rid of this. Okay, so now when we're talking about power supply rejection ratio, what you have to do is you have to look at both the plus and the minus. And this is very similar. We're going to be looking at a ratio of output, so it's the exact same circuit, one set up similar to how you would if you just had like a basic follower feedback configuration with no gain. You're biasing it at 1/2 VDD, and you actually want both the V plus terminals of both sets of circuits to be the same. The only difference here for the minus is that you're applying that AC signal to the ground or the V minus terminal of the op amp, where on this one you're just grounding that V minus terminal. So now if you run it, and this also takes a little bit of time, and we probe the output, and then we divide it by the output of the second. So here we're looking at 70, 80. I mean, really anything above 50 is going to be pretty good. And even all the way up to 1 megahertz, you're above 50. So this is actually a pretty good power supply rejection ratio. It means that when you're doing a mixed signal design where you have both analog and digital circuits combined into a single IC, that if you were to have this transistor-based design as part of that mixed signal, the switching that happens between the digital signals will affect the power supply, but that power supply fluctuation isn't going to affect the output of your op amp, which is what you want. So this is good power supply rejection ratio. But now we need to look at the plus, which is going to be the same thing, except now it's going to be a difference in voltage applied at VDD, or the V plus terminal. So we'll exit out of this. And that's exactly what's happening. So for this circuit, it's the exact same. We're just doing a basic follower, and because it's a follower, that's how you're getting the VAOL. Here we're stepping VDD from 4 to 6 in 1 volt increments, just like we always have. The only difference is here, we're going to be applying an AC signal to VDD and seeing how the op amp responds on the plus terminal. So let's run this. So this one's taking a little bit longer. Alright, so this is taking kind of an absurd amount of time. We'll see once it gets to when it's stepping the source to 100%. We'll see what happens. Okay, so now it's doing this like crazy fill-in thing, so I'm going to go ahead and halt the simulation. Failed to find DC operating point for AC analysis. Okay, so let's pull up the PSRR minus again. Okay, so I did go up to 100 gigaohms. Applied the AC source here. So I should just be able to apply the AC source there for the plus side. AC1. Oh, I'm stepping. Oh, okay. So I'm making the mistake of stepping. Oh no, but I should be. I should be stepping VDD, the same as this VDD, but with the AC source applied. Okay, so that's why it's going to take a little bit more time. So I'll just go ahead and run it again, and then I'll cut you guys to the end of this. Alright, so I finally got it to stop the simulation. But I also did it, but there's no DC component to this VDD+. And I'm slightly scared that I'm not getting a correct value. So maybe what I'll do is I'll set this to 5, and then I'll set the DC component to this as 5 as well. And I'll rerun it. There we go. Okay. And that's actually worse. But still not bad, because it's still above, 50 dB. When you're well past the audio range. So anything beyond that you're not even going to hear anyway, if there isn't good power supply rejection ratio. So I'll go ahead and leave the plus there. Maybe if you guys have the patience, you can run it. So I'm going to go ahead and take it back to the way that it was before, and maybe if one of you guys sims it while not running a screen capturing program, it'll work faster. So I'll go ahead and save it and exit out of it. But it looks as though the plus and the minus, the power supply rejection ratio isn't going to be an issue with this. And it isn't going to be an issue with it when you're simulating, because our, well, it's very controlled, first of all. But even when we're interjecting a signal that we don't want, it's getting rid of it pretty dang well. Let's go ahead and exit out of all this. Oh, and that's it for those sims.